So let me start by thanking the organizers very much for the invitation and the opportunity to be here. It's a very special occasion for me to be celebrating Srini on 70th. I had the distinct honor and pleasure to be his, in fact, one of his first PhD students at Yale. So I was able just recently to unearth in stacks of old photographs Hopkins. And so this was the attendees list. Quite a lot of people showed up. I'm particularly fond of this photograph where the invited speakers and the organizers were pictured. So you can see Srini here. Now the hair color has changed compared to the preceding picture. But you see Dan Joseph, who's passed away. Stephen Davis, Professor Arasima was there. I guess Dan Lathrop, you can see some others in this picture. Which, so again, great memories, and looking forward to the next one 10 years from now. And so let me now essentially go to the, so we will, after this wonderful preceding lecture in the very small scale aspects of quantum turbulence, let me kind of get back to classical turbulence, and I thought I would start with some kind of just very basic statements about turbulence, just remembering a little bit some of the phenomenology. So brief comments about nature of turbulence, again, the spirit of this being very introductory. But then the emphasis will be on modeling and large eddy simulations, which is what I will be focusing on, and I'll very briefly summarize Reynolds average Navier-Stokes direct numerical simulations in LES. I'll spend some time on perhaps a more fluid mechanical view of one of the main tools we use in computer modeling of turbulence, the notion of eddy-viscosity, which, as you know, is very classical, very old, and there's perhaps a fluid mechanical reason why it's been reasonably successful, in fact, perhaps more so than it's usually credited with. So I'll spend a bit of time on this, and then go a little bit more in detail about what's called the Smagorinsky model and the so-called full textbook, Tenekes and Lumley's. And so the book starts essentially by saying that turbulence is and has fundamental properties such as, for example, diffusive. So this kind of looks like perhaps an experiment in some kind of water channel, perhaps, where there's maybe on top of some kind of metal surface that's kind of reflective. So you see the shade of these injected dye or another fluid. It's turbulent, so it's very diffusive. It grows, it mixes very effectively. But turbulence is not just that, it's also property of a continuum, and it's multiscale. And this picture, as a matter of fact, I just fooled you. This is not in a laboratory tank with a kind of reflective metal surface. It's a photograph of fires following oil spills, and this is in fact the ocean surface. You can see the little ships here. And so I guess the sense of scale is important. We cover a lot of scales, the main theme of this conference. And obviously this is here we see the diffusion happening as well. In this case, this is a much higher Reynolds, it's a very high Reynolds number. Turbulence is multiscale, so these are other properties of turbulence that are worth remembering. Again, in terms of diffusion, you can also look at how a surface will be deformed and particles on the surface will be mixing together. This is a famous experiment done at Hopkins by Mike Carwhite in isotropic turbulence, the wrinkling of a surface. This is done on a computer using direct numerical simulation. Again, just figures of a diffusion of turbulence. This is not a movie. In fact, normally the mixing of cream and coffee is meant to illustrate mixing and diffusion as well. Here I'm asking you to imagine that you first stir it and there's some turbulence happening and then you just let it be. And obviously turbulence is also dissipative in the sense that kinetic energy is dissipated. So imagine on the decay of kinetic energy in these eddies illustrating the dissipativeness of turbulence. Another property of turbulence is it's irregular, it's rough. Again, I mentioned it's multiscale. This is a wonderful photograph, in fact, was taken by a friend of mine a few years ago in a rather dramatic eruption of a volcano. There's a preceding picture just in a few minutes ago before this one with eruption, and just in a few minutes, this gigantic plume rose. So this is in southern Chile. Luckily for the Chileans, the winds were blowing towards Argentina, so this whole thing went the other way, but this can cause, obviously, a lot of damage. Turbulence is vortical, and this is another one of the properties listed in Tenicus and Lumley. There's vorticity fluctuations, and it's three-dimensional. This is obviously now a very classic way of visualizing the small scales of turbulence. In this case, we're visualizing the magnitude of the vorticity square, and so it's a visualization of the famous Kolmogorov scale worms, tangles of turbulence. One other aspect that I think is quite noticeable is the fact that this is clustered. It's not the uniform, spatially uniform distribution of vortices. There are regions where there's more of them. Here there's a lot of them, and then there's these kind of more dead regions. This is associated with the kind of the multiscale structure of small-scale intermittency. If you zoom in here, and then you can actually create the following animation. So in the preceding talk, Professor Zubrek mentioned the tangling of quantized vortices that you can, in fact, coarse-grain them and look at them at bigger scales, and then, in fact, some more classical-like phenomena occur. This is an isotropic, this is from a direct numerical simulation of isotropic turbulence, where, I actually want to go back to the preceding one, this one. So what we've done here is we've filtered the velocity, calculated the vorticity, and generated, in some sense, coarse-grained vortices, and then looked at inside those vortices, the Kolmogorov scale, small-scale vortices, and you can see how they're grouped together, forming this larger scale one, but the larger scale is, in fact, twisting and stretching the smaller scale motions. Here you can see kind of a superposition of the same thing at three separate scales. So three-dimensional, time-dependent vorticity fluctuations. This particular one is not really in Tenicus and Lumley, but probably one might want to add it that there's eddies of many sizes in turbulence, but also there's presence of very large-scale coherent structures that are often very long-lived and are very visible in turbulence. And there's a lot of, obviously, a lot of very fruitful research in coherent structures that has occurred. In terms of applications, aerospace, combustion, environment, renewable energy. Tomorrow I will talk quite a bit about this one. Again, geophysics, environmental, astrophysics, going to bigger scales. So these are the things that you know. The simplest type of turbulence, as we know, is isotropic turbulence. I'll talk quite a bit about isotropic turbulence, as a matter of fact. Because as you will see, we will be, in fact, specifically interested in the rates of decay of turbulence. Turns out that's a really important aspect when we need to model turbulence. And this is generated in a wind tunnel. You can generate it with a grid. It can be a regular grid, or here we built an active fractal grid to inject turbulence at multiple scales. And then you have turbulence in the core here, perhaps, and over small distances that is statistically reasonably close to isotropic, and then as you follow the mean flow, it decays at a particular rate. This is obviously the canonical, simplest type of turbulence. So, in terms of describing turbulent flows, we know with this again in the classical world, we will focus on incompressible single fluid Newtonian fluids. So the Navier-Stokes equations, essentially F equals ma. Very familiar to us, and the three levels, the three classical, typical levels of modeling, if we are faced with a problem of predicting a particular flow, occurs at the following three levels. So direct numerical simulation, where we're resolving all the scales. At the other extreme, if we do either an ensemble average or for statistically steady state flows, time averaging, we are talking about the world of Reynolds average Navier-Stokes. And then what I will spend most of the time in is Large-Eddy-Simulations, where somewhere in between, where we keep some of the larger scale motions directly resolved on our computer, and we somehow are faced with a challenge of parametrizing the effects of the small scale motions that are not explicitly resolved on our grid. So that's what I will spend most of the time on. In terms of the traditional engineering approach, is a Reynolds decomposition. Obviously, it's over 100 years old, where you take the Navier-Stokes equations and you perform a linear operation in terms of averaging. Again, it can either be ensemble averaging or time averaging. Let's imagine we do time averaging for statistically steady state flow, so this first term here will drop. And essentially, the way this is, the simplest way to do this is to then essentially put an averaging operator on top of each of the terms and then rewrite the advective term by sums and differences, by essentially, I don't know what this T here is, by essentially putting the term that we used to have here on the right-hand side with a minus sign, so it's essentially the average of the nonlinear advective term, and then add and subtract on one side the product of the averaged velocities. And this is, of course, the Reynolds stress tensor that needs to be parametrized and is modeled in Reynolds averaged descriptions. Normally you will perhaps not have seen it, or it's not normally written in this way, but obviously using the properties of averaging, this expression, essentially taking the Reynolds stress to be the difference between the coarse-grained nonlinear, or the coarse-grained momentum flux minus the momentum flux due to the coarse-grained velocities, and those two things are obviously not the same, that difference can also be written as a covariance between the fluctuations. And so typically this is a more familiar way of seeing the Reynolds stress tensor. That's kind of all I will say about Reynolds averaging. Now it turns out, sorry, I'm kind of not doing this. So it turns out that to model this stress tensor, to model these correlations between fluctuations of turbulence, the internal structure of turbulent flow becomes very important. So now it really becomes important to understand how turbulent eddies, how different components are correlated, what are their length scales, what is the shape of these eddies. All these internal structural properties of turbulence enter in understanding this. And that's why we're also, from a pragmatic viewpoint, very interested in the spatial structure of turbulence. And there, the simplest descriptor of structure is the statistics at 2 points. And so the statistics at 2 points can be looked at by structure functions, where the object, the simplest object what we can build is the longitudinal velocity increment. So it's the difference between 2 points, velocities at 2 different points, and one of the components is the longitudinal one. The most famous object there is the structure function, so it's how much energy this particular velocity difference has, so that's the second order structure function. You can also talk about the spectral tensor. So if you take the Fourier transform of a velocity field, again, there are certain assumptions of homogeneity that are built into our ability to do this, but the spectral tensor defined this way, and then in isotropic turbulence, the spectral tensor can be expressed in terms of the isotropically averaged radial 3D energy spectrum. So those two descriptions are very useful. And again, in terms of the dynamics and the physics of turbulence, the simplest view is, of course, the Richardson-Kolmogorov view, where if we look at the rate at which the turbulence is receiving energy by the large scales, so the large scales will have, for example, the RMS velocity squared, that will be the kinetic energy at the large scales, divided by a turnover time, you get U cube over the largest scales of the eddies. That same reasoning, if you apply it at various smaller scales, gives rise to the notion of a cascade of energy, where the energy dissipation then takes place at the smallest scales in classical turbulence. Quantitatively, if that flux is constant, you get to the famous 2/3 law, or to the minus 5/3 energy spectrum. In terms of direct numerical simulation, I will not say too much about DNS either. Essentially, we are now able to do this at moderate Reynolds numbers. Depends how you define the Reynolds number, what particular number one wishes to quote as where DNS is possible. But essentially, if we are able to simultaneously resolve some small fraction of the scale of the Kolmogorov scale, as well as the system size where the large eddies are present, then we can do DNS, but at higher and higher Reynolds numbers, obviously, direct numerical simulation becomes impossible, and because we cannot afford a grid fine enough to resolve down to the Kolmogorov scales. So that brings us then to the realm of what's called large eddy simulations. where essentially we want to do a spatial coarse graining of the flow so that we can do simulations in a more affordable way. And so, for example, here, this is a DNS of 1,000 cube where you see color contours of a velocity. This has about 4 to the 10 to the 9 degrees of freedom. This is quite expensive to do. If I want to do a large eddy simulation of this, I might imagine first applying some kind of coarse graining operation on the spatial distribution. Could be some kind of spatial filter, for example, and bring this down, for example, to 10 to the 5 degrees of freedom. This is something that can be very quickly computed nowadays and is more practical if we needed to do simulations of some system where we want to vary a lot of parameters and do a lot of inexpensive simulations. This is feasible. At this level, it's not feasible. So that's the realm of LES. And here the research questions are, since we've gotten rid of the small scales, how do these eliminated small scales affect the motions at the larger scales? And that's essentially what's called subgrid scale modeling. I will, in terms of the nomenclature, I will use a tilde to denote filtered properties. And so in terms of deriving, or in terms of the mechanics, how you move forward in LES, you would again start from the Navier-Stokes equations and again define the filtered velocity. This is this coarse-grained velocity field as a convolution with some spatial operator. This is a filter, could be a spatial filter with a characteristic scale delta applied to this velocity field. And then very much like the ensemble averaging that we did in Reynolds averaging, we will apply this operator to this entire equation. And if you do that, then you essentially put a filter on top of this. Now, obviously, this is a time-dependent flow, so we cannot get rid of the time-dependent term. The nonlinear term here now is simply filtered. Here I'm using the fact that the spatial filtering and the derivatives will commute. There's some technical details there. That's not always the case, but typically it is. And so the other terms just get this tilde on top. Now, this is, again, just like before. It's just going to be rewritten by writing this filtered momentum flux as in terms of the product of the filtered velocities, and the difference between the two is put on the right-hand side as the divergence of a stress tensor, and this is so-called subgrid scale stress tensor. And so, again, it has exactly the same physical interpretation. It is the difference between the momentum fluxes when you take the actual momentum flux and you coarse grain it, and you subtract from it the momentum flux that you would have gotten if you had used the filtered velocity, the coarse-grained velocities, to evaluate the momentum fluxes. So that's the basic quantity that needs to be parametrized. Obviously, this is an unclosed quantity. If you want to put it in this equation to solve this on a computer, we need an expression for this. And here, again, now I'm going to essentially just summarize the simplest possible approach, which is to say that the deviatoric part of that stress tensor, so the isotropic part of the stress tensor typically can be absorbed into the pressure, so it doesn't really have any dynamical effect. The deviatoric part of that tensor is then typically can model if we choose to model it with an eddy-viscosity assumption, then it's expressed in terms of the velocity gradient tensor, the symmetric part of the velocity gradient tensor, essentially that these stresses are going to be proportional to the rate at which the fluid at the large scale is being deformed. And in front of this is an eddy viscosity, the subgrid scale eddy viscosity. Now, the big question, even if we accept this, then is, of course, how much is this eddy viscosity? Now, dimensionally, the usual arguments go, this is going to be some length scale multiplied by a velocity scale. So we need a length scale. In large eddy simulations, if your filter scale is in the inertial range or not too close to the integral scale, that does provide a length scale. So typically we pick that as the length scale, and then a velocity scale needs to be picked. And by the usual arguments of closure theory, it has to be things that are Galilean invariant, so it can depend on the velocity of the frame and so on. So some norm on the velocity gradients or velocity differences is the best approach, and so you can take the norm of the symmetric part of the velocity gradient tensor, multiply by this length scale. That will give you a velocity scale, and so this gives you delta times the absolute value of the strain rate as the the quantity that the eddy viscosity is set proportional to, and then there's a dimensionless parameter in front that, represents our ignorance of the problem, and that needs to somehow be determined. So this, in terms of the history, this was put in place in the 60s and 70s, starting really in the meteorology community. The names that really started this, Joe Smagorinsky, in fact, this model is called the Smagorinsky model. He had, in fact, proposed this first in two-dimensional simulations, but then it took off in 3D simulations rather quickly. Doug Lilly provided quite a bit of the more theoretical underpinnings of this. In fact, a lot of the things I'll talk about are really motivated by his paper. And then Jim Deardorff started really applying LES very seriously to boundary layer type, channel type flows and atmospheric boundary layers. So that's really all. It's a rich history. There's a lot of things that have been going on, but I'm not going to talk too much about the history. So again, one of the big questions is how big is CS? If this physically were to make good sense, one would hope perhaps that CS should be of order 1, the non-dimensional quantity. If it's too far away from 1, maybe it may not be entirely right with this model, but let's see how big this coefficient should be. Now, before I get there, there's another aspect of the effects of the small scales that is perhaps the most important one, which you can see by looking at the energetics of the large scales. So what I'm showing here now is the transport equation for the kinetic energy of the large scales. So you derive that equation in the usual way, and there's going to be some transport terms, dissipative terms, and the term that we'll talk quite a lot about is the so-called, what's called the subgrid scale dissipation, which is the contraction of the stress tensor times the large-scale velocity gradient. If this quantity is, in parentheses, if it's positive, then it's a sink of large-scale kinetic energy. It's also, of course, a source of small-scale kinetic energy, the kinetic energy in the scale smaller than the grid. So let me just put this little cartoon here showing what we're really doing in LES from a spectral point of view. So we have the spectrum of turbulence, we have some cutoff, we have some grid, which will hopefully fall somewhere here. Typically, the length scale, the wave number associated with the filter scale is essentially inverse to the filter scale, pi over delta. And this term here, the ensemble average of this term is essentially the flux, the spectral flux that we're used to thinking in turbulence, the rate of energy that is being extracted or from the large scales and it's being injected into the small scales. And so one of the things you can just see here already is that the statistics of the kinetic energy at the large scales can really only be predicted correctly if we are extracting kinetic energy at the large scale at the correct rate. So this, whatever we do with our subgrid model, whatever we replace tau with, it better be such that it will generate this flux correctly at the correct rate. Okay? So this is probably the most important element one wants to make sure in a subgrid model. Here is something that kind of perhaps an addendum to that thought is you can from the Navier-Stokes from the filtered Navier-Stokes equations. Similarly to the derivation of the von Karman-Howard and the Kolmogorov equation, you can repeat that exercise, and for isotropic turbulence, you can define or derive a sort of 4/5 law for the large scales in large-eddy simulations. And if you do that, you show that the third-order structure functions of the large-scale velocity fluctuations, again, this is the 4/5 law, but instead of the molecular epsilon, we obtain here this subgrid stress mediated flux of energy in the inertial range. And then there is this additional term here that can be shown to really be relevant only at scales close to the filter scale. And this is so this is kind of not unlike the viscous term in the original equation, but this is now entirely in the inertial range, and it represents correlations between the stress tensor, the subgrid stress tensor, and velocity increments at that scale. And so so in some sense, to get the statistics of the large scales correctly in LES, one can show that there really is a hierarchy of conditions that you want the model to reproduce. The most important one is that the correlation between the stress tensor and the strain rate be such that you get the right extraction of kinetic energy. But there's more advanced conditions, such as here, for example, that this two-point correlation, there's going to be a term here that has the stress at one point times the velocity at another point at a distance r. That two-point structure between the stress and the large-scale velocities also should be predicted correctly. But again, let's go back to the simplest one, which is how big should this parameter be? And of course, you can see the simplest model, the simplest approach to make sure that we get a controlled amount of dissipation is to set the stress proportional to strain rate. And this will give us a quadratic norm that we have we have some control over. And so again, the Smagorinsky model provides precisely that with a sign such that this will be a positive quantity for sure. So this is probably the simplest approach to really guarantee that we're going to have some amount of dissipation, and then this parameter might in fact help us control how much we will have. So so how big should CS be? How strong should this eddy viscosity be? And this is a derivation by Doug Lilly in the mid-60s, which is quite nice. So I will walk you through this in some detail. Hopefully it's not too many details. So essentially, we postulate, right, that we have some kind of equilibrium, that this flux of energy here ultimately has to be equal to the dissipation rate that will go out at the small scales. Then you replace the subgrid stress tensor by the Smagorinsky model, and you essentially get that epsilon is equal to something that can be expressed in terms of the norm of the large scale velocity gradient tensor. And then in front here is the Smagorinsky constant, the scale, and so on. Right? So we need to evaluate this second moment of the strain rate tensor. There are some subtleties here. If you look carefully, what I have in this parenthesis is a third order moment because I have SSS. So this is this is a cubic moment, but it's positive definite, right? And here I've written it as the average of the square to the 3/2. So again, if you're into things like anomalous scaling and intermittency, you will already see that I've made a big assumption here. At this step, I've, for example, neglected effects of intermittency. So now so the task is to evaluate the second order moment. This can be expressed in terms of the derivatives like this. Then you go into Fourier space and you express it in terms of the spectral tensor. Again, that's why I had mentioned to you that we are interested in the two-point structure precisely because we need it in cases like this. So we do have, assuming that the small scales are locally isotropic, we assume that we can use the isotropic form of the energy spectrum. So we put it in here, you do the calculation, you evaluate it, and this entire, this S squared is essentially proportional to epsilon to the 2/3, and then there's a pi over delta to the 4/3 because I've integrated only from the largest up to the filter scale, right? Because this is the filtered velocity gradient. So when I perform these integrals, I go from 0 to pi over delta rather than 0 to infinity. So this is how this term arises. And then you take this and you replace it here. So you have to raise it to the 3/2 and you put it back in here. And essentially, you replace it here. And what the things cancel very nicely. And you can essentially now relate the Smagorinsky coefficient with the prefactor that entered in the radial energy spectrum, CK, the Kolmogorov constant. The measured value of the Kolmogorov constant being close to 1.6 or so gives you that the Smagorinsky coefficient, according to this and according to Lilly, ought to be about 0.60. So this is a nice way of calibrating the eddy viscosity for locally isotropic turbulence. Obviously, we need to know what the Kolmogorov constant is. So this is empirical knowledge that's been built in. So before I go on and talk more about the validity of that value of the coefficient and how generally applicable it is in various types of flows, let me make a few remarks about eddy viscosity. Okay? So we go back to this functional form that I put up, and if you read many books on turbulence and so on, the common justification for it is simply to say, well, eddy viscosity assumes that we view turbulence as we view, for example, kinetic theory of gases, where you have where you obtain a linear relationship like this between the stress and the rate of deformations by looking at small deviations from the distributions, and then you do a Chapman-Edstone expansion, and the first terms, you do get these kind of things from that perspective. And essentially then people say, well, this assumes that the small-scale eddies of turbulence, we're treating them like random molecules in a random gas. And so there's this assumption somehow that we are using kinetic theory analogies to build eddy viscosity, which is very often how it is justified. And if you look at a turbulent flow, that doesn't sound that convincing. One could say that turbulence is not like a can of sand that we shake, but it's perhaps more like a can of worms, that you shake it and inside things are happening, and there's these worms rotating and some memory and so on. So taking this into account, let me just go over a few steps that provide what one might term perhaps a more fluid mechanical rationale or basis for what we call eddy viscosity. So for this, I kind of need to step back a little bit, and I will do this really in the framework of Large-Eddy-Simulation. So we will be talking essentially about filtering things, and there's a cutoff scale, and what I need to predict is the deviatoric part of the stress tensor. And so again, this is the quantity that we want to predict. It's close to, again, there's a J missing, the kind of covariance tensor of the fluctuations. And so that is one object. Later on, when we're towards the end of the derivation, the object that I will in fact be really wanting to describe will be the conditional average of this local covariance tensor, given that the large scales have a certain velocity gradient structure. So A is going to be the full velocity gradient tensor at the large scales, and what I will want to predict is the conditional average of this. This can be shown to be, in some sense, the best statistical predictor of the subgrid stress. So this is the object I would like to predict, and we will not use analogies with kinetic theory of gases. So instead, we will use the following. So imagine I have the small scale. So U here, U prime is some representative small scale fluctuation, and imagine the flow. It is a vector pointing in a particular direction, and imagine that this region of the flow, the large scales are such that there is a velocity gradient tensor A tilde. So this fluid is moving, and it's subjected to the large scales straining and rotation of the large scales as represented by A. So Aij is du dx, essentially, the full velocity gradient tensor. So one of the things, for example, a material, a sphere will, as you move along with the fluid, will be deformed, might generate kind of an ellipsoid like this, and this fluctuation will rotate, and vorticity will stretch, and so on. In terms of the momentum equation, if I write both the large and small scales, I can write something like this. On the right-hand side, I have the forces, so this has pressure and viscosity and so on. In fact, I will make a lot of assumptions and simplifications, and you will see where. So this is, again, the full left-hand side. I can put together, if I'm only interested in the equation for the fluctuation, I can combine the time derivative here with this advective term that has a U tilde here with this one to form the Lagrangian derivative of the fluctuation. And on the right-hand side, I will have the linear term, which will have this U prime times the large-scale velocity gradient. And so this will be this term with a minus sign. And then on the right-hand side, I will have the forces, the fluctuating forces, and so on. Okay. We will do what one could call kind of an even more simplified version of rapid distortion theory, where we completely get rid of all the forces. I'm going to neglect all the forces. I'm only going to take into account the effect of the large-scale gradient in terms of its essentially kinematically both rotating and stretching this velocity fluctuation. I'm going to imagine I get rid of this term, and essentially this remaining equation simply looks very simple like this, and essentially represents the fate of fluctuations in the presence of a large-scale gradient. Okay? And so vorticity stretching, for example, is included here. One of the most obvious effects of this is if you have if you had vorticity stretching with a direction, it'll stretch in the most stretching direction. It will spin up, and the fluctuations in the direction perpendicular to the most stretching direction will go up. And for the velocity, therefore, there's this minus sign here. Anyway, that's so again, this is still kind of very simplified, almost kinematic fluid mechanics. So if I follow this in time, this has a very simple solution in terms of matrix exponential. So the u prime at some later time will simply be the matrix exponential of this. Now, the second assumption I'm making is that A is slowly varying. So I'm assuming that A over this time that I'm going to integrate this has not changed. Otherwise, you have to make this a little more complicated. But I'm going to assume that this A in this kind of neighborhood for a certain amount of time is so slowly varying that I'm not changing it. So again, now I'm putting in this notion of separation of timescales. And then this is again the initial condition here. And then if let's say I don't continue for a very long time, so you can, this can be expanded and form, this is the expansion of the matrix exponential. So now I need to assemble the stress. So I'm going to take this dyadic product. I'm going to take the product of this times the transpose. So here's the transpose. And now I'm going to evaluate this conditional average. So now I need the conditional average of this quantity. But because it's conditioned on the large-scale velocity gradient, this can go outside of the averaging. So this term here, again, I've done this short time approximation, is outside of the averaging, and I only have the conditional average in terms of the initial condition inside here. So this u prime and this u prime is our conditional average at the initial time. And now this is the sense at which I think the eddy-viscosity models assume isotropy. If I assume that the expected value of my initial condition, which happened some time ago before I'm interested in where I really want to predict the stress, if I assume that that is isotropic, so I assume this is an isotropic tensor, so it's just going to be proportional to the identity, and of course it has to have units of energy, so I will construct units of energy based on the scale and the velocity gradient itself, then I replace this with the identity, and then you put the identity here, now you simply get this term, and you get that this full stress becomes the identity minus, and here you have A plus A transpose. And that brings us to this twice the symmetric part of the velocity gradient tensor. So very naturally then, if I assume that I've pursued this evolution over time scale TA, that becomes my eddy viscosity, and the tensorial structure of the stress is in fact proportional to the strain rate. That from this argument, essentially following fluctuations that get tilted and deformed by the large-scale velocity gradient. I haven't really made any statistical assumption on kinetic theory of gases. So I just thought it'd be kind of interesting to mention this other interpretation, which might be what eddy viscosity isn't as bad as one might think in many cases. So going back to the problem of how large should this coefficient now be? How large should this Smagorinsky coefficient be? Let me show you a few things that one can do. One can, for example, interrogate data to measure it. So, for example, if you can measure the stress tensor, you can measure the average rate at which energy is dissipated in the inertial range, and you can compare it with what, for example, the Smagorinsky model would have predicted, and take the ratio of the two, and that will be your empirically determined Smagorinsky coefficient. That's what we did theoretically for isotropic turbulence. Here's, for example, this is quite a few years ago, where we measured this in a physical experiment in the atmospheric surface layer together with NCAR researchers. So we measured filtered cities, gradients, and evaluated the Smagorinsky coefficient as a function of, for example, the stability of the atmosphere. So, for example, here, this is 0 here was for cases of neutral stability. This is stably stratified, and unstably stratified would be on the left. So this is the measured Smagorinsky coefficient as function of delta over the Wonin-Obuchov scale. So as you could see, near neutral for scales that were kind of far from the surface, we approached this 0.16 value that we had to derive for isotropic turbulence. But if you have stable stratification, for example, that parameter really has to shrink dramatically, has to be reduced. So more in general, you really have you have to allow for the Smagorinsky coefficient to depend on physical properties, perhaps on position and time as well. I think the one very typical example also is, for example, transitional flow, where if you have a laminar flow, you don't want that coefficient to be 0.16. Initially, you want it to be 0, so that you're not extracting any energy and you allow the instabilities to develop. Close to solid surfaces, that coefficient needs to be also smaller to account for wall blocking effects. So this is, I wanted to briefly describe what I consider quite an important development for large-eddy simulation, which is the dynamic model. This was proposed in the early 90s by Massimo Germano, who was then at Stanford, visiting Stanford, and this gave rise to quite a lot of research in that particular area. So let me go back now and tell you about this from a spectral viewpoint. So here's the energy spectrum again. Let's assume that this is our grid filter. So this is this filter where I have the tilde denoting our variables. And again, to the right of this line is the subgrid stress tensor. I guess if this is energy, then this is really the energy, the trace of it. But you can imagine this represents all the smaller scales represented by this subgrid stress tensor. And to the left is everything that I'm resolving in LES. And what Germano realized was the following. Let us assume that we will do a second filtering. So we will now do a further coarse graining. Okay? So instead of just coarse graining at one scale, let me coarse grain at another scale, and that other coarse graining I will denote with a bar. Okay? And so then one can construct the following identity. So it's always nice to show identities by showing the left and right hand exactly equal. So on the left, both this term and this term is essentially the momentum flux that has been coarse grained at this scale and then at this scale. Okay? So I'm coarse graining twice, so to speak. So I'm effectively coarse graining at this scale. All right? And then minus, and what I will have here is the coarse grained velocity at this scale, and then forming the momentum flux of that. So this is the subgrid stress that you would have built if you were doing the simulation at this scale. It's kind of written a little bit kind of with an extra tilde. So this is obviously an identity, right? Because the left is exactly equal to the right. I've left a little bit of a hole here because I'm going to now put in something that adds up to 0, right? And so I'm going to add and subtract exactly the same thing. So what I'm adding and subtracting, however, is an interesting term because it will be the momentum flux that is caused by velocities at this scale, and then that momentum flux is coarse-grained at this scale. See? So I'm going to essentially form this. I add and subtract, so it's still an identity. But now I can reinterpret these terms differently. So I think so I can interpret these terms differently because now this difference is this. You recognize the stress tensor, the original one, at this scale, which is just coarse-grained at this scale. And this is a new tensor, which is called the resolved stress tensor, or it's also called the Leonard stress, following Tony Leonard, who had built similar approaches in the mid-70s. So this stress tensor is what you would have built from these velocities by test filtering it at this, by filtering it at that scale minus the full difference. And so what we have essentially is, visually, it's a very easy identity to see. What we're writing is that T, which is the subgrid of this entire range, including both scales, is equal to tau, which is this part, plus L, which is this part. And so visually, essentially, I'm just saying T equals tau plus L. That's what this says. Okay? And then now the rest are technical details, how exactly you formulate this. But the basic idea will now be to replace this stress tensor by the Smagorinsky model, replace this stress tensor by the Smagorinsky model in another scale, and using this identity, noting that we in fact know this tensor during the simulation. So Lij is a known quantity when I do a simulation at this scale. Okay? And so the idea will be to use that online during the simulation to determine what the right parameter is by essentially making a consistency condition with the simulation. So we take this identity, we write it like this, then there's several details that we don't really need to look into details, but Smagorinsky model at large scales gets put for T, at small scales for this one, the parameter, this parameter C is let's assuming is the same at both scales. That gives you an equation that can be solved online. Now the question, now the details come in, and in some sense, even results depend on exactly how you do it. One thing you see immediately is that this is a tensor equation because I really have 6 independent equations. These are symmetric tensors, and I have a single parameter CS. And so it's an overdetermined system. And so one approach that was immediately proposed, in fact, by Lilly was to do a least, solving that parameter in a kind of least square sense. And if you do a least square minimization with respect to this parameter, you find that the Smagorinsky dynamic coefficient will be the ratio of these averages of these tensors. All of these can be determined during simulation. So essentially what this would say is that we are measuring CS by sampling, as we do the simulation, sampling the simulation at the bigger scales, which in LES we have available. We measure CS, and then we assume that it's the same CS for the smaller scales, and then we apply them at the next time step, if you will. And if the simulation, if the flow was spatially homogeneous, for example, decaying isotropic turbulence in a box, this averaging is best done over the entire volume. For things like boundary layers or channel flow, things that are homogeneous in two-dimensional directions, for example, you might do an averaging over planes. I think I will probably just go to the last few slides here. Let me show you 2 more variants of this. So there was a lot of activity working with this dynamic model. As I mentioned, there's one big assumption that we've made, which is that the Smagorinsky coefficient is the same at the so-called test filter and at the grid filter. Right? We assumed that those would be the same. That allowed us to get a single equation. If the filter scale approaches the integral scale of turbulence, as it actually happens when you do high Reynolds number boundary layer simulations, where you're not really resolving down to the logarithmic region, and even then, at very close to the wall, you always have the grid scale close to the integral scale. And so this assumption that the coefficient is the same at both scales cannot hold any longer. So in this case, we've generalized the approach, and you can end up with something called the scale-dependent dynamic model, in which case the way to do it is to include yet another filter scale at an even bigger scale, and then sample the large scales to learn about how that parameter changes as a function of scale. And so in practical implementations of that, you do 2 test filters at 2 different scales, you obtain parameters at these 2 different scales, and then you extrapolate to smaller scales to determine the coefficient here. So that was one generalization that's been quite helpful, in particular for applications to atmospheric boundary layers, where again, close to the surface, we are really not in the inertial range. And this assumption that the parameter was the same really did not hold out. So that has been very useful. And then the other approach or the other assumption that was very hard in general to apply is the assumption that we have directions of statistical homogeneity. So if you do channel flow, you can average over planes and so on. But if you do a more complicated flow, we found that it would be better to do a time averaging. But time averaging, you can't do it at a fixed point. You have to do it following fluid trajectory so that you end up with Galilean invariant formulations of the model. And so that has led to what's called the Lagrangian model, where this averaging is essentially done following fluid trajectories. So that's really the model that we've been using. And let me perhaps close with one visualization of a large eddy simulation that uses that subgrid model as kind of, this is my last slide, and this in some sense motivates my presentation tomorrow, which is applications of LES to renewable energy systems. So this is a LES that was done by Richard Stevens when he was a postdoc at Hopkins. And this represents wind turbines in an array in the atmospheric turbulent boundary layers. In this case, the grid size is about 10 meters. We are parametrizing. We need to parametrize all the smaller eddies smaller than 10 meters, of which there are many down to, in the atmosphere, close to millimeter. But we are able to resolve up to maybe the largest scales, up to about 1 kilometer in height and several kilometers in the horizontal directions. By the way, these are volume renderings of low velocity regions in the wakes, and then we've just distributed tracer particles in the just to show the wakes behind each of these turbines. Again, if we diagnose very carefully what that Smagorinsky coefficient is doing in a simulation like this, it is very complicated. It would have been very difficult for us ahead of time to say, okay, we will use a coefficient that has this value at this location and so on. We find that it's very, it is low near the surface, as one expects, but then it's very high, in fact, very close to the rotors due to these shear layers. And so non-trivial behavior that we weren't really able to, we wouldn't have been able to predict ahead of time. Whereas here, we're just letting the computer do this kind of flow analysis on the larger scales that we're resolving and then telling us what the parameter is. So I hope this has been a somewhat useful glimpse in terms of connecting turbulence theory, basic phenomenology, and then all the way to when we need to actually make flow predictions. So sorry, this is the slide I wanted to end with. The other one is for the talk tomorrow, but and I'll be very happy to take any questions. Thank you very much.
Question? Yes, please.
Thank you for the stimulating talk. I wanted to ask that in your matrix exponential model, how do you quantify that TA thing? Because
yeah, that's a very good question. So in practice, we just said it's going to be some turnover time at that scale, and we ended up using the same Smagorinsky type thing, where it's delta times S. So we use delta and we use S to generate a time scale. But the logic behind it is essentially, you have A generating an environment that will take fluctuations and will somehow stretch them and make them grow and so on. And then turbulence has other pressure strain and other effects that will kind of try to maybe make this like this. The typical turbulence models look at this and find this level by making a balance between production and dissipation and setting the unsteady term 0. In a nutshell, what we're doing here is we're looking at the time scale here and getting this level by multiplying the slope times this time scale. And so your question is quite, what is that time scale? And that's where, again, the empiricism comes in. It's essentially turnover time that's estimated in the usual way. But this reasoning gave us insight into the tensorial structure, how these vectors and tensors would evolve.
Would you bring this fact into the model straight away, or rather than just changing the value of the Smagorinsky coefficient?
Yeah, very good question. So when we do simulations with a dynamic model for stable boundary layers, for example, we find that indeed the dynamic coefficient is reduced, automatically. I hate to say automatically, but because the large scales are explicitly affected by stratification. So what happens is at the larger scales, that turbulence is already damped by the stratification, and that leads to a reduction in the parameter. But it's not quite at the correct length scale. But if we do the scale-dependent one, it's a better result. So yes, it has that effect, but it's not built in through a formula, but through this dynamic procedure.
It's in continuation of the same question. In stably stratified flows, the Kolmogorov flux decreases with wave numbers. But for unstably stratified flows, it kind of constant or slightly increases. Your plot seems consistent with that. The flux is decreasing, the CS is lower. But for unstable stratification, I saw only few points.
Yeah.
And they seem to be kind of flat to 0.16. Is that correct?
Yeah, we did not have that much data at the left. You're correct. So when we do the simulations, though, as I think what you're saying is that the Smagorinsky coefficient we get, the dynamically is about the same as for isotropic turbulence. It's for the stable one where we see this decrease.
Well, towards the end, you showed how you actually can make separate more than one scale.
Yes.
Now there are some of these limiting flows where the large scales in one part of the flow may be very different from the scales in another part of it. Wall jet is a very simple example. Can that be handled by large-eddy simulation? Because in that case, actually the eddy-viscosity turns out to be negative in certain regions.
Yeah, the state of subgrid modeling also with dynamic models for cases when there's an inverse cascade or where the filter size is right at the middle between the two regimes. So my quick answer would be, I can't say that you cannot do LES, but this kind of model would not be able to handle it and shouldn't, because indeed, as you say, you get the wrong sign of things.
Okay, looks like that's the end of the questions. Thank you very much for the very nice talk.